Hello. How are you doing, Glory? Good to see you. I see you're having a little bit of a connection issue, perhaps. Don't worry, this will be recorded. Hello.
Hello.
How are things by you?
I'm good. I'm good. And you?
Good. So what's your daily routine like when you have class? What are you doing right before this and what do you do right after?
Um, Before class, I'm usually getting up around 8 o'clock, consistently 8 o'clock. Make breakfast, um, kind of prepare class, kind of watch any old lectures or part of any old lectures, just to kind of refresh for class. And after class, around after lunch, typically I go to the base for about 3 hours, maybe 1 to 4, 12:30 to 4, and see what I have to do there.
Oh, nice.
And then of course after that I go work out or something like that.
What about tending to your car?
Uh,
You had
well,
mentioned in your intro that you were really hot on
yeah.
cars and working on them.
Well, yeah. Looking well now. I guess I'm in the process of kind of looking for a modification that I want to do to my car. Um, they can be pretty costly though, and I'm really just trying to save money because I really want to do it. I'm really just trying to
Gotcha.
save money and see what I actually need to do and what to buy to kind of get that going with the modification. But other than that, with the car, everything's been going good. It's almost a year that I've had the car now, so that's pretty good.
You'll have to share some pictures with us at some point.
Yes, sir. I do like
We've
taking pictures of it too.
we've got such a small class, and we're going to end up being cohorts and contacts for a very long time, hopefully.
Yep.
Um, Isaac, you and Shepard, I see you've come in. Glory was on a little while ago, but I think she may have had some connection issues. But this is all being recorded, so we should be okay.
How are you, sir?
Okay, so I'm going to go ahead and get started in just a second. Last time we had talked about the land biosphere and the atmosphere interactions. And can anybody tell me what the two main interactions were between the land biosphere and the atmosphere?
As far as like the rock,
As far as
land,
CO2
and
goes, the exchange, what regulates the amount of CO2 in the atmosphere, carbon dioxide. Shepard, you want to go ahead and take a stab at it?
Hello,
Shepard,
Prof.
go ahead.
I didn't get the question clear.
So the question is, last time we talked about the land biosphere and the atmosphere and the processes that regulate carbon dioxide in both. And so there were two processes we really talked about, and I was wondering if you could name what those were that help regulate the amount of CO2 in the atmosphere.
where you kind of um going towards the process of photosynthesis within plants? Okay.
Yep, that's one of them,
Okay.
photosynthesis in plants.
Okay, I had a different concept in mind. It was
Uh-huh.
Then
photosynthesis.
respiration
And
and
respiration.
growth.
Right, right. So those two are roughly balanced. They're not balanced all through the year. There's when does one dominate over the other?
That's for
Photosynthesis.
photosynthesis. That's in summer.
Right. Spring and summer.
Photosynthesis in summer. Then
Right.
respiration in winter.
Right. Absolutely. Over a year span or a 2-year span, you'll find that they're roughly balanced. The amount of CO2 going into the atmosphere and the amount being from respiration and the amount being taken out by photosynthesis, averaged over the year, the two balance out. And if you've got an apple or any piece of fruit around you and you take a look at it, you hold it in your hand, just a few months ago, what makes up that apple or that fruit, all of that is carbon that was in the atmosphere. Once you eat the fruit, you're going to use the sugars that are in there. Remember, the sugars are made of the carbons that came from carbon dioxide to get energy. And as you burn through those sugars and get energy, one of the byproducts of that will be CO2, which will be released back in the atmosphere. So on net, it's a zero-sum kind of game. You've got about as much being released as you're being put in. Now, also last time we talked about the oceans. What role does the oceans play in the amount of CO2 that's in the atmosphere? How does it regulate or have anything to do with the CO2 in the atmosphere? This is from what we talked about last time.
Hello?
Yeah.
The oceans actually accommodate about 43 gigatons, or 45,000 gigatons, and it takes a lot of time. It takes years before it is released into the atmosphere for circulation.
Okay, that is true. But remember, we divided the ocean into two regimes, two layers, if you will. Can anybody tell me what the two layers were?
We have the mixed layer and also the deep oceans.
Right, right. And the mixed layer, is the one that readily absorbs carbon dioxide because, again, carbon dioxide readily dissolves in water. And that exchange, can go back and forth to the atmosphere. The ocean can degas and release the CO2 back into the atmosphere, or it can take the CO2 that it's gotten and mix it with the deeper ocean. And then once it's in the deeper ocean, it's going to be stuck there for a lot more time. Let me go ahead and share what we're talking about here. Okay. So we're on to lecture 15, and today we'll be talking about the land, atmosphere, ocean, and rock interactions. But just as a reminder, what we talked about last time is, there's an exchange of CO2 between the atmosphere and land through photosynthesis and respiration, and between the atmosphere and the ocean, with CO2 dissolving into the ocean and degassing out of the ocean. But if it gets into the ocean, it's getting in at the mixed layer, and that can exchange with the deep ocean. And what I'm showing here are the resonance times for carbon in each of these places. So if you've got a molecule of carbon, if you breathe it out, for example, it'll probably stay in the atmosphere for about 4 years. And then from there, it will either go into the land biosphere, which it could be incorporated into the land biosphere. Like, you eat an apple, a lot of that carbon and those sugars become metabolized in addition to getting the energy out of them. Some of that carbon goes up to make up physically what you are. And maybe when you pass away or later on, etc., those molecules really will be released back into the atmosphere. And so it can stay on average around 20 years. If it goes into the ocean, it'll probably spend about 5 years in the mixed layer, and then it could return to the atmosphere, or it can go down to the deep ocean. So you must know this in terms of where the CO2 is going and what's regulating the CO2. When we talked about climate, and we talked about what greenhouse gases are, remember in our climate models, if you have a layer of an atmosphere that can absorb infrared radiation, then it will re-radiate both out into space and down to the ground, heating up the earth, bringing up its temperature. And so those gases which can absorb infrared are the ones that we're most concerned about. The largest of which, remember, is water vapor. There's not much we can do to regulate water vapor in the atmosphere. And the amount of water vapor in the atmosphere has to do with a lot of different processes that don't deal with mankind. And considering how our climate's been for the last 10,000 years, there wasn't that big of a change. But what we do see is that carbon dioxide is the next biggest effector as a greenhouse gas. And carbon dioxide, as we'll see later, is something that we do have a profound effect on. And so that's why now we're focusing on, where does carbon dioxide reside in the atmosphere? How does it get there? And how does it get out? And so when we move beyond this carbon cycling, we find carbon also cycles with the rocks. So you've got the atmosphere and land biosphere interactions, the atmosphere ocean interactions, and now we have atmosphere and rock interactions. And mostly those, does anybody know how CO2 gets from the rocks to the atmosphere? That sounds like a weird one, right?
Yes,
Yes,
Prof.
Prof.
From
Through erupting,
volcanic
let's say
eruption.
volcanoes.
Yes,
Okay.
volcanism is exactly what we're talking about. And so we're talking about 0.1 gigaton of carbon per year on average. And this is averaged over many years for volcanic eruptions, because some years you have them, some years you don't. When you do have them, it might be larger than 0.1 gigatons, but that's averaged out for the years that you don't have a lot of volcanic eruptions. And so when these volcanic eruptions happen, they're spewing lots of stuff into the atmosphere. Besides dust and rock, they're spewing carbon dioxide, as well as some sulfates and sulfur dioxide and a few other nasty things. But it's responsible for about 100 megatons of carbon each year going into the atmosphere. How do we get CO2 out of the atmosphere and back into the rocks? Because if we only go in one direction, then the rocks are always going to be adding on to the amount of carbon in the atmosphere. And given how old this planet is, we should have tons more CO2. So how does the CO2 get back into the rocks? It's okay. It's okay if you don't know.
No, Prof.
Is it rain?
Is it what?
Maybe. Is it through rainfall? Maybe. Snowfall and rainfall.
So yeah,
Precipitation.
that has a lot to do with it. We know that carbon dioxide readily dissolves in water, right? We talked about that with the deep ocean. When it dissolves in water, there'll be a slight chemical reaction, and it will form what we call carbonic acid. And so I've got the chemical formula shown here. You know, and this is reversible. Carbonic acid can turn into CO2 in water as well. So the arrow really goes both ways. And when it goes back into CO2, you know, if we're talking about the ocean, that's when it can degas, right? And the solubility of CO2 in water is about 1 gram per liter at 1 atmospheric temperature. So, you know, if you take out a liter of water from the ocean at the top, you'll probably have about 1 gram of CO2 that's turned into carbonic acid. Now, if we get too much of this, if we're adding too much of an acid, if we make too much of an acid in the oceans, that's going to cause acidification, right? Lower the pH. And lowering the pH can be harmful to coral, and acids can eat away at minerals used by oysters, clams, and a variety of different ocean organisms. So too much of that is bad, but it is a normal process with the normal amounts of carbon that we've got in the air. But as you mentioned, this CO2 can dissolve into raindrops as well. So when the rain is falling, it's going to naturally dissolve into the raindrops. And again, we're going to form this carbonic acid. Well, as they hit the rocks, combined with the force of the rain falling down from, you know, miles in the sky, as well as the carbonic acid in them, they'll start to chemically react with the rocks as well as weathering just due to the pressure. But certainly that force of hitting of the drop hitting the rock helps chemical reactions happen because it's supplying energy for these chemical reactions. And so you'll start to get chemical reactions with the rocks. Specifically, if you've got something like calcium sulfoxide, and you have the CO2 from the carbonic acid, that can turn into limestone or chalk. And so our main process for getting carbon dioxide out of the atmosphere is through this chemical weathering. And so you can have naturally occurring minerals that will react with the CO2, usually when it's in water, dissolved in water, because then it's in its acidic form. And that can form silica, which is calcium carbonate, and that's where the carbon is, as well as silicon dioxide. And so this often is known as limestone, the calcium carbonate. And here's a picture of some natural limestone deposits in Italy. Also, the rainwater with the carbonic acid in it can flow into the rocks and flow into the ground and slowly seep in. And so what I'm showing you here are some pictures of some limestone deposits on the floor of caves through a process called speleothem, which you don't really need to know the name of the process, but understand that when water is dissolved that contains this calcium carbonate, seeps into the caves, over time, these deposits can build up and form these limestone formations. So all of this, the carbon in these rocks, has all come from the atmosphere. And there's a variety of different, I'm not going to go through all the different minerals that will react with carbon dioxide or calcium carbonate or carbonic acid, but know that there are a lot of them. So dunite, for example, will react with CO2 to form silica, magnesite. Basalt readily reacts with CO2. It will form dolomite and calcite. I've included some pictures here of those minerals. So really, there's this big exchange between the rocks spewing out carbon dioxide in the form of volcanic eruptions. And now you can kind of see why those volcanic eruptions spew out carbon dioxide, because remember, hot heat, pressure, it's melting these rocks under a great amount of heat and releasing that carbon in the form of carbon dioxide. So during our volcanic eruptions, and then the atmosphere will then take carbon dioxide out of the air through chemical weathering. But understand that the chemical weathering, that process for any appreciable amount of carbon, happens over geological timescales. We don't see mountains just build up overnight or over a year or two. We're talking millions and hundreds of millions of years that it's taking for these raindrops to pull carbon out of the atmosphere. So chemical weathering really occurs on geological timescales, quite large, quite long. And that's something really important. That's fundamental to understanding climate change is the amounts that we're dealing with and the timescales that we're dealing with for the exchange of atmospheres into the what we call the rock reservoir. Okay. Now there is one other way to get to the rock reservoir, one other exchange, and that comes from buried organic material. So in the land biosphere, you know, like we've talked about before, an organism can die, and in the process of its decomposition by various fungi and bacteria, it will re-release carbon in the form of carbon dioxide in the atmosphere as well as methane. But some of the material gets buried before it can actually decompose and release the CO2 and the methane. And if it gets buried and more material is thrown on it, and more material is thrown on it, and it continues to get further and further buried, now you have all this weight, all this pressure pushing down. And that's a form of energy, and that kind of energy can also instigate chemical reactions, provide the energy for chemical reactions. And so this pressure and this heat tends to change that organic material. A variety of different kind of chemical reactions will happen, but usually what you're seeing is dehydration reactions. They're pressing these organic compounds, mostly sugars that these organisms are made out of. Plants are made of cellulose, which is just a long chain of sugars. And as they're being crushed, water molecules are being released, and you start forming, double bonds with the carbon, or just hydrogens remain. And this creates what we call hydrocarbons, because they're mostly carbon and hydrogen chains. So there's ethane, propane, butane, pentane. Those are mostly gases. But as you get to longer and longer chains, like if you get to heptane and octane, both of those are liquids at room temperature. And I think you all have probably heard of octane before. Caldrian, I know you, where do you hear the word octane?
Octane fuel.
Yeah, so that's what's in gasoline. It's always what percentage of octane is it? That's the fuel in the gasoline, right? And basically what it is are these carbons with just a bunch of hydrogens on them. Octane means eight, means octa. And so that's just an 8 carbon chain with hydrogens attached to it. Similarly, you see the same kind of processes in the formation of other hydrocarbons like coal. So you can imagine a swamp. Now, this process takes time, right? A lot of time, okay? So think back to 300 million years ago when there were some plants, say, that died, And rather than being consumed, they ended up getting buried. Okay. They got buried under the dirt and the swamp. More dirt was thrown over them. Over millions and millions of years, more and more water and dirt accumulated over them, forming this great amount of pressure. And when there's enough rock and dirt above it, there's enough pressure, this plant material is going to turn into coal. And so chemical reactions are the same that we talked about before. So right here, this is cellulose. And again, remember cellulose, they're just chains of glucose connected in a variety of different ways. And they've got hydrogen bonds between them or whatever. But remember, glucose is carbon chains with OHs, with oxygens and hydrogens. But when you push them together and you apply this pressure, you're going to squeeze out those oxygens in the form of water molecules and hydrogens, leaving behind a material that's mostly carbon with some oxygens. But the longer it stays, the fewer oxygens will be stuck in that molecule, and the more it will just be a hydrocarbon. Okay. And so this is kind of what you see over a long period of time. And so this is what coal looks like, the chemical structure for coal. It's very similar to cellulose, only with, it's been dehydrated. Water molecules have been pulled out, oxygens and 2 hydrogens have been pulled out of this, leaving behind some double bonds and mostly hydrogen and carbon. But again, this process occurs over millions of years. This doesn't happen overnight. If you leave something dead in your yard, sitting there, you can come back tomorrow, it'll still be sitting there. You can come back in a year and maybe it's still sitting there. Maybe it hasn't even gotten buried, but even if you bury it a little bit, it's just going to be a little bit under the earth, right? That's not enough pressure to do anything. It's going to take millions of years for more dirt to accumulate on top and rocks, right? That's really going to give that pressure that it needs. So we see the same thing with natural gas formation. Here a common pathway is in the ocean, where 300 to 400 million years ago, tiny sea plants and animals died and fell onto the ocean floor. Over time, they're covered by layers of silt and sand. And over even more time, they get buried under more silt and sand and more dead bodies. And it takes a long time for enough material to accumulate over them that there's enough pressure and heat to actually start causing the chemical reactions that will dehydrate them and turn them into mostly carbon compounds or hydrocarbons. And so this is where we get natural gas from as well. This is some of the hydrogen that's released as well. And it's also where we get oil and gas deposits from. So this is just another, and to give you an idea of the complexity of these deposits, here's a schematic from that's used in crude oil refining. So when you pull oil out of the ground and you want to separate it into its components, you'll really find that stuff, as you would imagine, they're not all carbon chains of one length. There's a whole variety of different molecules that were smushed down and ground up by this heat and pressure. And so you would expect that the products have a variety of different chain lengths. So things with 1 to 4 carbons are going to be gases. Things that have 5 to 10 carbons are going to be liquids. You can give it even a little bit further up in the carbon chain to have them still remain liquids, but they'll be very viscous. So you can see up here, there's gases, Um, this would be like gasoline would be in this category. Okay. Kerosenes would be also in that mix. There'd also be like diesel fuel and lubricants like motor oil, and all the way down to almost a tarry substance. You know, that these are long carbon chains, so they're very, very viscous, almost to the point of being solid. Okay. And so this is kind of the range of what all that stuff is being compacted to. Now, remember, this was all living biomaterial about 400 million years ago, right? So when you're burning fuel in your gas tank, you're burning up carbon that was probably, you know, in a dinosaur last before it's seen the atmosphere again. And there's a variety of different hydrocarbons, you know, that are created in this process. Here's some of the composition of natural gas and those gas deposits. This is usually the kind of stuff that you'll find in there. And you can see there are all these hydrocarbons, right? And so this bearing of organic material is another important way you remove carbon from the land biosphere. But again, just like chemical weathering, it's taking place on very long time scales. Okay, very, very long time scales, hundreds of millions of years. Not thousands, not hundreds, not tens, hundreds of millions. And so what we find is if you look at the amounts, the buried organic material going into the rocks and the chemical weathering putting more CO2 into the rocks, more carbon into the rocks, balance out roughly over geological timescales with volcanic eruptions. So again, it cycles around through this, goes into the rock, stays for a long time, and then it comes out at about 0.1 gigatons per year. Okay. So what does that mean for us? What does that mean for what we're doing now? What we've created in the modern age is we've created a new flux. So this is what we're seeing here right now. These are the natural fluxes that are relatively balanced. But what we've done is we've created a new flux, humans have, and that's the burning of fossil fuels. Okay, here we're digging into the ground. This, I'm sure this is all stuff you know, but the chemical reaction that we're talking about here is the same one basically that we were using for respiration. You're going to have a hydrocarbon compound. Actually, for respiration, it was carbon, oxygen, and hydrogen molecules combining with O2 to make CO2 in water and release energy. In the burning of fossil fuels, we're taking hydrocarbons. That's why I have the X here, because the chain length can vary, and you know, as in the case of coal, it became kind of complex. Mixed with oxygen is going to, and that's the fire part of burning fossil fuels. Remember, oxygen is needed to for a flame. That's because it's part of the chemical reaction, and that's going to create CO2, a little bit of water, and also energy. And that's the energy that we use to run our power plants, that power our houses, turn on the lights, and charge our phones, or whatever we use, you know, electrical energy for. Most of it right now comes from the burning of coal. Okay. So it's the same chemical reaction, but now, you know, as respiration, but now we're taking it from the rock reservoir. And that's the crucial piece. We're taking it from the rock reservoir. If we were burning plants, we'd have the same, that were grown recently on ground. We'd have the same chemical reaction. We'd release CO2, but it wouldn't be a problem because we'd be taking from the land biomass. In order to have recently grown that plant, we would have had to have taken an equivalent amount of CO2 out of the atmosphere that we're now putting back into the atmosphere when we burn it. And so the cycle remains balanced. We're just taking more out of the atmosphere and putting more back in. And the more of extant plant materials or biofuels that we burn, the faster carbon cycles, but it's still staying balanced. We're taking out as much CO2 as we're putting back in the burning of, whatever biofuels we're talking about. So the key to understanding our problems with climate change is that we're coming from this rock layer and we're pulling out of the rock biosphere. If we were coming out of the land biosphere layer, not a problem, because there'd be two arrows, one going there and one coming back to show how much CO2 we need to make that biofuel, right? And we're putting a lot of stuff into the atmosphere. We're burning lots and lots of stuff. One of the figures I saw in the book was about 10 gigatons of carbon that we put into the atmosphere every year. What was the amount that goes from the rocks to the atmosphere through volcanism? Does anybody remember? We just covered that number a little earlier.
1 gigaton.
It wasn't even one, it was 0.1 gigaton. So we're putting 100 times more carbon into the atmosphere than normal volcanic eruptions, than the normal flow of carbon from the rock reservoir to the atmosphere. The burning of fossil fuels, we're doing it 100 times faster. Now, it took hundreds of millions of years for those organic materials to be buried in the first place and turned into fossil fuels. And we're going to burn it all up in just a few hundred years. So instead of the millions of years that it takes to put that amount of carbon back into the atmosphere, we're putting in 100 times that amount very quickly. Okay. We're releasing carbon basically 1 million times faster than nature is sequestering it. And that becomes the problem, because if you have more arrows going into the atmosphere than you have coming out of the atmosphere, if you have more flux of carbon into the atmosphere than you have coming out of the atmosphere, there's nothing for the atmosphere to do but absorb it. And then it increases. And we know from our favorite equation that we covered, when we were doing our climate modeling, that final equation that says as you increase the number of layers of the atmosphere, you get more additional warming. Adding CO2 is like increasing those layers. Okay, here's just a little schematic of these natural gas resources that we're talking about, that we're releasing 1 million times faster. Now, there's one other thing to mention too, that's also something new that happens because of humans, and this is deforestation. So we know that as part of removing CO2 from the atmosphere is photosynthesis. But if we remove trees and plants through deforestation, that's going to change the amount of CO2 that can be pulled out of the atmosphere. And we call these changes land use changes. And they've increased the rate into the atmosphere by about 1 gigaton a year. So that's something kind of important to know. So we have all these different things going on. And so what this has led to, as you can imagine, is the amount of CO2 in our atmosphere has been increasing. This is going from 1960 to 2020. This is parts per million. It was at about 320 before, and it's at about 410 parts per million now. Remember that number, that's going to be on exams. And if you go back to the pre-industrial revolution, in the early 1800s, it was at around 280 parts per million. So we've almost doubled it since the Industrial Revolution. And as I mentioned before, we've come up with this formula that shows as you increase the number of layers, the temperature of the surface is going to increase. If you increase the number of layers in the atmosphere, now we're going to see that. Remember, we had a 1-layer atmosphere, then a 2-layer atmosphere. If you had a third or a fourth, the number of the layers determines how much the temperature is going to increase, assuming that you have the same albedo and the same constant. So any thoughts on that? So probably what you knew without seeing it, laid out in this fashion, but any comments? Questions? Okay. So,
Prof.
Okay.
Yes, concerning the petrochemical,
Mhm.
concerning the petrochemical fraction, I didn't see bitumen. I don't know whether it's not part of it.
Bitumen? Is that what you
Yes.
said? It's definitely hold on a second. So that's that's a form of petroleum. So that's in there. We may not have used that word, but it's a semi-solid, almost tarry form of petroleum. So when we were getting into that layers of the tars, bitumen would have been in there. Okay. So these are the levels since the 1960s of CO2. Okay, so the past 60 years. This is the amount of CO2 that we've seen in the atmosphere, and you can see it's rising, right? Now I'm going to put onto this graph how much CO2 we've actually put into the air. And that's the second line here. That's how much CO2 that we've stuffed into the atmosphere based on the rates that we're burning it. But yet we only observe this amount when we measure it. And that's about a difference of about 50%. So right now, we should actually be up at about 500 parts per million. I don't know why this is on parts per, okay. Right now, instead of the instead of the amount that we're seeing now. So this is the amount of increase that we're putting into the atmosphere. Okay, this is how much we've added, and this is how much we've observed. Can anybody explain why we see less than we've put in? If we've pumped all this carbon dioxide in the atmosphere, now we go to measure it, we don't see nearly as much. Why is that?
Does some of the CO2 dissipate within the atmosphere through natural occurrences such as rainfall and other weather patterns?
Well,
Some...
what are our carbon cycles? So what are the ways you pull out carbon? You go into the land biosphere doing photosynthesis, you dissolve into the oceans, and you do some weathering into the rocks. Now, is weathering into the rocks going to make much of a difference on this graph?
Nah, it wouldn't be noticeable. It'd be pretty much negligible.
Right.
Looking at the graph.
So the stuff being pulled out by the rain is going to be negligible because the weathering occurs on geological timescales, millions of years, right? So we're talking most of this carbon is going to the land biosphere or to the oceans. Okay, we only observe half this amount because we're going into the land biosphere and we're going into the ocean. One of the effects that you'll see, and this is a measured effect, is that when there's more CO2, when the concentration of CO2 is larger in the atmosphere, plants will grow faster. It's easier to do carbon fixation if one of the chemicals in the chemical reaction, if one of the ingredients in the chemical reaction is in greater abundance, the chemical reaction can happen faster. You see that in general chemistry, the Chatelier principle, for those of you who remember chemistry. And so we call this CO2 fertilization, okay? By having more CO2 around, plants will grow faster, and so they'll pull out CO2 from the atmosphere faster. So that's the increase going into the land biosphere. Us pumping in carbon dioxide doesn't into the atmosphere by burning fossil fuels doesn't cause additional plants to grow. It doesn't plant more plants. It doesn't plant more people or things that I guess it would just be plants that do photosynthesis. But what it does do is allow the plants that are already there to increase their effectiveness at pulling the CO2 out. Now, when it concerns the ocean, higher concentration of CO2 allows for more CO2 to dissolve into the ocean, okay? But since this is above, the normal levels, that would mean since CO2 turns into carbonic acid when it dissolves, that means we're increasing the acid concentration in the ocean, okay? And so if you add up this CO2 fertilization and ocean acidification, that's about half the total amount. So that's why you see however much we put in, within a few years, about half of it is going to be taken out. Let me give an example of this. I think it's easier to understand with an example. So say I put a huge carbon pulse into the atmosphere. I released a ton of CO2, okay? What you would first expect to see is that about in the beginning, because there's more CO2, more is going to dissolve into the ocean, and you're going to have the CO2 fertilization increasing photosynthesis. So about 50% of that additional carbon will go into land biosphere and the ocean mixed layer, okay? And we know how fast it takes to exchange with the mixed layer. The deep ocean, that takes a lot longer, right? But this entire process of pulling out this half the additional carbon takes about 40 years. So if you're burning fossil fuels right now in your car or in your lamps or anything like that, about half the carbon you're releasing in the atmosphere is going to be taken out of the atmosphere in about within 40 years. Some of it will be ocean acidification. Some will come out in increased photosynthesis. So here's like a little plot. After 40 years, we've come down to about half. This is the carbon pulse. It's the amount of carbon that we've added, and this is how much is remaining, okay? So after a while, you're going to get to a point where you saturate things. The ocean's not going to be able to absorb more carbon. There's a saturation point. Same thing, you can only increase photosynthesis so much, okay? So now we're going to have to rely on other parts of our fluxes. So the deep ocean can take some of the CO2, carbonic acid, out of the mixed layer and put it down into the deep ocean, right? But that process takes a lot more time, okay? And so when we look at going into the deep ocean now, we're talking, so we were at 50% after 40 years. It's going to take us about 600 years to remove, so we were at 50% after 40 years, that's up here. So to remove an additional 30%, it's going to take 600 years. Okay. So if you burn that fuel in your gas tank or in your lamp, half the CO2 will be gone in 40 years. Another 30% will be gone in 600 years. But now at this point, we've filled up those reservoirs, okay? And the only way we're going to get anything more out of the atmosphere is by going into our final remaining reservoir, because now we've used up the deep ocean. We've used up the mixed layer. Now we're talking about when the deep ocean is saturated, we can only go into the rock reservoir, and that takes thousands of years. So you can see, here's our theory. There's this phase is transferring to the land biosphere. This phase is transferring to the deep ocean. And finally, this phase, which can take up to 10,000 years from now, the gas that you release from burning fossil fuels, either in your gas tank or in your lamps or what have you, 15% of that is still going to be around 10,000 years from now. That's big. That's a lot. I mean, that's how long it takes, right? I hate to end on a really sour, bad note. I came across this article while I was putting together things for this talk. It was a neat carbon storage experiment. It was tied to geothermal power plants in Iceland. 90%, what they did is they injected CO2. They first put it into water, and they injected that into some mineral deposits, and they found out that 90% of the CO2 was mineralized in just 2 years. So that was pretty cool. So there is a way, if we've got carbon dioxide there, and once it's in the rocks, we know how long it's staying in the rocks, right? For a long time, it's done. So there is hope for ways that we can hide the CO2 and get it out of our atmosphere. There's a lot of different chemical reactions with rocks. You can take dunite, that'll turn into silica, and magnesite, basalt, which is what they did in this one. And by the way, I have the link down here to that article. But basalt, which is what they use, will turn into dolomite, calcite, and magnesite. So cool stuff. And it turns out, here's another article, since I found that interesting. This is showing a lot of mineral deposits that could be used for CO2 storage around the world. And there's an article for that one as well. And all that's posted in the PowerPoint file that will be up on Moodle. And I'll email it out for everybody. Was this an okay lecture? We doing okay here? I see smiles, so I guess we're finally talking about stuff you find interesting instead of all that stupid power stuff. Black body radiation. Hate it.
Yeah, that was interesting.
Gloria, you had mentioned to me in an email you'd like to go over some of the power stuff and some of the equations. Why don't I'll shoot you off an email, or you can shoot me off one, and we can maybe make a time tomorrow to do one-on-one to talk about it, because I got to get to my next class right now. But if anybody wants to chat one-on-one, always happy to do it. Just shoot me off an email. We can work a time. But thanks a lot, everybody, for coming to class. I really enjoy it.
Thank you, Prof.
I will,
You're not proud.
and I'm going to put into the chat those articles. Here's one. I don't think I got both of them in there, but here's one of them. Have a great day, and I will talk to you on Friday, if not before. Oh, don't forget, start working on those peer teachings on building a climate model. I want to see you do those layers of the atmosphere. Now you know why they're important. Think of each layer as carbon dioxide that's absorbing that infrared. I mean, it's true that it's also water vapor, but the one where the point is, as you add more layers, it's like adding more carbon dioxide. We'll talk then. Thanks. Bye-bye.